Bonjour tout le monde, donc Cédric SAUZEAT, comme vous le voyez je suis de l'ENTPE et j'ai le plaisir de vous accueillir, nombreux, donc merci à tous d'être là. Donc je suis chargé de vous présenter l'étude de l'endommagement des enrobés bitumineux soumis à des cycles de gel-dégel. C'est ce qu'on a fait dans le cadre d'une thèse, celle de Tran Duc Tang, entre Eurovia et puis l'ENTPE, et tout ça cofinancé également par le PN DVDC. Faut appuyer sur quel bouton là? Non. Non plus. Voilà. Il arrive, c'est le dernier, toujours. Donc pour le plan de la présentation, je vous donnerai quelques éléments de contexte, mais rapidement. On parlera des matériaux qui ont été testés, du conditionnement qu'on a fait subir aux éprouvettes, et puis des essais réalisés, et je vous présenterai quelques résultats. Donc évidemment, c'est des résultats de thèse, donc je ne serai pas exhaustif, et je vous renverrai aux mémoires de thèse si vous voulez plus de renseignements. Et voilà. Donc pour le contexte de l'étude, je vous disais que ça s'est déroulé dans le cadre du PN DVDC. Donc dans le cadre du PN, il y avait une étude qui était dédiée au mécanisme de dégradation des chaussées, et il y avait un sous-thème qui concernait les dégradations hivernales. C'est dans le cadre de ce sous-thème qu'on a réalisé la thèse, donc de Duc Tang Tran, entre l'ENTPE et Eurovia, et donc évidemment cofinancé par DVDC. Donc l'étude de l'impact des cycles gel-dégel sur le comportement des enrobés bitumineux. Donc rapidement, j'ai ces schémas un petit peu compliqués, mais qui ne le sont pas tant, pour vous présenter les objectifs de la thèse. Donc l'objectif de la thèse, c'était d'étudier, on sait comment se comporte le...
Sorry, what happens to the material? Sorry, my mic was off. So, which proves somebody's listening. And so, which means that we can see the different materials and their behavior, sorry about that, and the number of cycles to a few to millions of cycles, and for the vertical aspect, it's the amplitude. How does this evolve? Once we have, we thought we would damage the material by applying the effect of the water, the freeze and thaw cycle, and to see how what happens with older material. So 3 types of behavior: linear viscoelasticity, where we're going to solicit material in a very minor way and with not too many, with a very limited number. For fatigue, will not have too much pressure, but will do millions of cycles. And then what really interested us was the couple between thermomechanics during what we call the retreat of thermal behavior. So we tried to use a BSG 010M class 2 material with a bitumen of 50-70, and we aimed to have a material that contained 8% of hollowness. For the making of the test tubes, this was pretty classical. For the lab work, we used material that was either older or not, aged or not. We make it, we compact the plaques. We take about 40 samples, and for the older material, we age the material using the RIEM method, which was used in other tests, generally speaking. And when you have to and before compacting the plaques, so we did it by using a kiln, 135 degrees for 4 hours, 9 days, at 85 degrees. And then we made the samples or slabs with a rolling wheel compactor. And then for the conditioning or packaging, we used the samples and then we conditioned them. And during that time, we continued to have monitoring of the mass and the volume, and I'll show you that this was important to do this study. And finally, the third phase was the thermomechanical test. In front we had the material that we wanted for the simulation. For conditioning, there were different conditions for the samples. Here's the methods that we used. We saturated the samples when we had to. Then that was done in a vacuum. Well, it's not obviously what happens in a road, and we wanted to have a maximum amount, and that we did it in a vacuum, so that we had freeze-thaw cycles, -10 to -15 to 10 degrees, and then we had to make the conditions more difficult, and we went up to 50 degrees to raise the temperatures in terms of their resistance to water. So we went from -15 to 50 degrees to see the effect of high temperatures, and even we no longer froze the sample between 10 and 50 degrees. We all varied the number of the cycles, 10 or 50 cycles for freezing and thaw cycles, and you can see the sample that we kept in a low temperature container, and we had 7 centimeters of water to make sure we didn't have too significant saturation. For the trials, we used the ENTPE laboratory resources. We had complex studies on cylindric samples with the sensors that we use, extensometers and non-contact displacement sensors, and to also have the radio and to have access to the various samples. That's a classical way of doing it, and we'll be very happy if you want to come and visit the lab. Now, for the complex modulus test, we have different levels of temperatures, and we will look and have cycles with varying the sequences. The idea is to have a relatively low amplitude, 50 micrometers, in terms of deformation. I forgot to say, for the fatigue tests, we use the same mechanism, except for we'll be at 10 degrees, and we'll solicit the material with deformation levels which are smaller but different. And to see when we have breakdown, and to look at the life cycle of our sample, and then we used another thermal stress restraint thermal strain restrained specimen, TSRST. Something to test the teeth is a little bit smaller, 60 millimeters in diameter, and a little higher, 225 millimeters. And so it's the axial, where we maintain at a constant temperature during the entire test. And then when you cool the sample, tends to want to contract. We then do not allow them to do. And so then at one point we have breakdown, and that's the value to evaluate, to see the covering by comparing the temperature between samples and the cracking at the end. We separated in two campaigns for the experiment. The first was for the study of freeze and thaw, and we had another one where we do cycles to have high temperatures. The idea is to use the sensitivity to water tests, which are generally used, where we will heat the sample to very hot temperatures. Why did we do that? While we were doing the trials, we saw that there wasn't that much difference for freezing and thaw. But when we did the same thing with high temperatures, we have strong effects on the materials, and the effects we wanted to show, it wasn't of freezing and thawing that was put the pressure, but it was the hot temperature, in fact, that was more significant. That was for the experimental campaign. You have the list of the trials and the conditions that were applied for new and aged materials where we applied cycles of freezing thaw for dry and saturated materials, the number of cycles that varied, and then at the end of the freeze and thaw, sometimes we dried or tested it in still humid, and so you have the whole campaign. Now, I would like to now present some of the results of the CESE. It's going to be complicated to present everything, so I just want to give you some insight so that I respect my time frame here. You have on the bottom, you have time, and on the vertical part is the measure of saturation of the sample. So you look at the left, on the vertical axis, that's when we'll saturate the sample, which has a degree of saturation that's close to 0. And by using our method of saturation, we went rather high because we had levels of 70% at the highest level. This was maintained, and that's the horizontal part before the vertical. They're maintained even during the period when we froze the sample saturation, and we keep saturation at 70%, and then looked at the drying of the specimens or the samples. And if you look at the green line, there's a degree of saturation which goes down quickly but doesn't go to 0. That's if you leave your specimen, which allows it to dry at ambient temperatures. But if you saturate them, then the red line, for example, or yellow, you see that you have saturation which is much quicker, and at the end of 5 days, you're below 5% of degree of saturation. That's because we dried these samples in.
We were able to observe other results as well. After 6 months in an office, the test tubes basically also became dry. And in addition to that, we saw that desaturation was a lot faster if we hadn't carried out the freeze-thaw cycle, if they hadn't gone through the freeze-thaw cycle. So what about the conclusions that we could draw? First of all, let me stress that we were able to achieve quite a high degree of saturation, above 70%. Also, the drying method under vacuum that we were able to adopt, it was pretty effective. It enabled us to test the test tubes pretty quickly, not to have to hang around and wait for quite some time. However, the fact that we measured or monitored the evolution of the test tubes throughout this packaging phase, we were able to highlight the fact that in a vacuum, the products changed thanks to the freeze-thaw cycle. The products changed in quite a considerable manner because for test tubes, for example, samples with about 8%, they evolved because in the vacuum, they amounted to about 10% following on from the vacuum. So there was a change of approximately 2%. It's important to take into account the value, this value. You can't just use the initial value that you obtain prior to the packaging or the conditioning, because that can have an impact on the behavior of the material. Let me now refer to the results achieved thanks to the complex module. You're about to see a certain number of curves. I hope you're not going to be frightened, otherwise you won't dare to leave. Even for caribou eaters, I hope I'm going to be clear, the caribou eaters at the back of the room. This is a challenge that somebody had given me. I had to pronounce those words. So, concerning the complex model results, here you have a clear illustration with the cold plan. What is this? It's the complex module that is the real part and the imaginary part, because it's a complex module. you have the vertical axis that corresponds to the imaginary part and the horizontal plane, the real part. If you're not interested in this, if you're more interested in the module, just take the distance between the origin and a point in the curve, and then you've got the standard module that you're familiar with. So at the top, we've got the materials that we test in a standard manner, and at the base, the other products that were aged. You can see the blue curve is a bit closer to the horizontal plane, and this is due to the aging process that change the viscous capacities of the materials. The initial results that I want to show you involve no freeze-thaw cycles with the test tubes. Then further down the line, we had the freeze-thaw cycles. The test tubes were saturated, then they were frozen and thawed, and then they were dried before we carried out with the tests. And this is what happened with the freeze-thaw cycles, with 50 of them in total. It would seem that there were a few changes that were not significant for the non-aged materials. And then when we continued with the cycles, as I said, initially speaking, whereby we carried out, or rather where we took the temperature higher during the cycles, or cycles where we had freeze, then high temperature, or high temperature and then cold temperature, but without freezing. Here we obtained curves that, if you look at them closely, they look as though they can be overlaid upon one another perfectly. So we might tend to say that there's no impact of these cycles on the behavior of the materials. However, this is without taking into account one of the parameters, which is the void parameter or the vacuum parameter. And I've tried to materialize this on the lower graph. Look at the lower graph and the maximum value for the module. You have the vacuum value that you can look at right at the bottom. Whereas if you look at the vacuum level that is very small, it means you increase the module. So if you take into account this parameter, well, it means we were capable of normalizing the curves. And when we normalized the curves, we displayed very clearly that the impact of the hot-cold cycles or the hot freezing cycles, well, they have an impact on the materials that we'd forgotten. We can see the impact very clearly. However, on the materials that had already been aged, the fact that we heated them up again to 50 degrees during the course of the cycles, well, the fact that we'd aged the material initially meant that we didn't see the same impact. There was no impact of these cycles, particularly for the hot cycle. Next, concerning the freeze-thaw cycles, we weren't able to illustrate anything, and we saw no change to the materials, no significant change. So all of this was analyzed thanks to the viscoelastic module, and it basically enabled us to obtain all of the experimental results and to analyze these curves and normalize these curves. Just a few pieces of information on parameter 0. The highest module that we can have in terms of materials, the very high frequency and then very low temperature. You can see the evolution of this module that was measured based on the vacuum content. And the vacuum content does have a strong impact on this parameter, so it's important to correct the results that we obtained, taking into account the value in a vacuum and the value no longer in a vacuum. And you have an example here where you can see that the 0 figure drops for a module that started out at about 40,000. So in percentage terms, it's quite considerable. Cédric, you have 5 minutes left. 6. Please give me 6. Okay, no problem. So the second test was for thermal stress restrained specimens. Now, let me see whether I've got a laser pointer. If you look at the curves that are presented here, you can see the standard evolution during this test. And you can see the stress that increases based on the temperature. You've got these curves here. These are the curves for 0.6 freeze-thaw and so on and so forth. And as you can see, the curves tend to be on top of each other. The results vary a tiny bit. Here you've got the standard evolution of the materials. This is at the bottom of the graph. In the second left-hand table, you can see the volume-based evolution, and it's all pretty linear. The deformation is quite linear. At the same time, basically, as you carry out your elasticity test, the radial deformation is reduced, and so the diameter of your test sample reduces as well. And these are tests that we did on samples, test tubes that hadn't been dried and that still contained water. So here there are two different curves that appeared. The first curve is this one here, and you can find it very quickly go back to the standard evolution. And the other curve that appeared was the chaotic evolution here, where you can see that it zigzags up and down. It's the traction stress. There was traction stress that sometimes is compressed, and then all of a sudden it moves upwards. At minus 18 degrees, it starts to follow the same trend as the rest of the materials. What conclusion can we draw from this? Well, this chaotic evolution, let me say, this is an aside. It's the same for the radial deformation. Well, for the different curves that were saturated but that had gone through the thaw and freeze, if you've got water in your materials, you freeze your test tube, the water tends to freeze as well. And so as a result, it dilates in your test tube. And then your test tube, instead of going into traction, it goes into compression, which is pretty logical. Ice has an impact here. And after a certain amount of time, you reduce the temperature, and hence you get the normal behavior pattern once again. What happens afterwards, and that is less normal, it's all of this until it freezes at minus 18. And this test tube, in other words, is saturated, but it hasn't gone through the freeze-thaw cycle. So compared with the test tubes that went through the thaw-freeze cycle, it has a difficult type of behavior. The first freeze-thaw cycle it sees is the test you're running. And this is where you see that the water freezes gradually in the test tube. And we allocate this to the fact that when you've got water in the pores, depending on the pressure that you can have in these pores, you get a freezing temperature, or rather a water temperature, that drops, and that can drop as far as minus 18 degrees. We've seen this for different types of clays, for example. And this is where you have this phenomenon, and this is why you've got it in this test tube. So the conclusion we draw in relation to this is as follows. There was no impact. You've got the performances that are given for the materials 0, 5, 10, and then tested with freeze-thaw. The major evolution you see is for the damp materials, and the fact that they haven't gone through the freeze-thaw cycle beforehand, it means that something happens the very first time the product is frozen in your test tube. So let me move on to the fatigue results. We'll be very brief here. We carried out fatigue tests also. Here you've got the vertical axis for the deformation, and then the horizontal axis is for the number of cycles. And as you can see, there's no real difference for the materials that are tested, whether there have been 0 freeze-thaw cycles or 50 freeze-thaw cycles, and depending on the saturation tests. This brings me to my conclusions, and it'll be virtually my last slide. I think it will be my last slide. Concerning the complex module, what were we able to measure? Well, once you use your test tube when it's dry, that's what we were interested in. You won't be able to highlight an impact from the freeze-thaw cycle. We had up to 50 cycles, and we saw no impact on the viscoelastic properties. The only differences that we saw were when the test tubes contained water. And of course, when you've got water, water freezes. And even for the more complex tests, we saw an increase to a certain extent of the complex module. For the thermal stress restrained specimen test, in the same way as when the test tubes are tested dry, there's no significant impact of the thaw freeze cycle when they're tested and they're saturated. Here you can see the fact that you've had a first freeze thaw cycle, it completely changes the behavior of your test tube. And what we imagine is that it must have dilated the pores where the water was located, whereas the fact that you've got water in the material and the fact that you haven't dilated the pores, then the water isn't free to freeze as it wishes, and it has to reach much lower temperatures before the test sample is able to freeze completely. Next, for the fatigue tests, along the same lines, we didn't really see any significant impact of the freeze-thaw process or saturation. Whether the sample was dry, damp or saturated. That's what I wanted to say about the few results. Of course, within the scope of the project, a certain number of reports have been drafted. So I do invite you, if necessary, if you require any extra information or if you've got any questions, please do read these articles or read the PhD thesis report. And we also took part in the optimization of these results, having them published, etc. My 6 minutes are up.